To achieve this vision as primary aim to develop a suitable technology to detect and mitigate the risk of landslide in hilly terrain, via utilization of advanced earth sensing and retaining techniques and eye-based warning systems. Our system is composed of artificial intelligence, machine learning, Internet of Things, smart materials and sustainable design, besides fostering preparedness about built environment vulnerability under natural calamities and developing resilient structural techniques to minimize the losses. With that, we present our system called Early Warning Landslide Detection.
In order to study landslide behavior associated with earthquake shaking, physical model tests such as shaking table tests are desirable. It is very important to have thorough understanding about the initiation mechanism of an earthquake-induced landslide for the purpose of defining slope failure. We, at the Department of Civil Engineering of JUIT University Solan, have an in-house horizontal shaking table which is very much suitable for simulating the earthquake shaking conditions for lab-scale slope models. A flume model was prepared in our department for experimentation and was mounted and fixed properly on the shaking table, keeping in account the angle of repose considerations. The soil slope was chosen to be inclined at an angle of about 34 degrees with the base. Our testing was focused on cohesionless soil that was locally available, and the same was used for preparing the flume model. The soil slope was laid and compacted in layers. The overall compaction was targeted to achieve a value of 1.4 grams cm3.
The model was homogeneous throughout and the effect of vegetation was not considered as we are in initial phase of our research. A hollow stem was installed inside the soil up to a depth of 0.2 meters from the top layer. It incorporated all the necessary sensors in it for recording the changes happening in the soil internally as well as externally. The test was successfully conducted at our lab and required data was attained. Considering the fact that it was the first physical test in our research process, we had a real positive outcome. In future, we will be conducting many more with better flume models and better instrumentation. Extensive testing on various parameters will be done in coming days. Early Warning Landslide Detection Project is a system that uses multiple sensors and other IoT devices to monitor the movements and changes in soil conditions in areas prone to landslides. The project aims to provide real-time data on soil stability, moisture levels, and other factors that may contribute to landslides. The system typically consists of several components, including sensors placed in the ground to measure soil movement, temperature, humidity, and other environmental factors. These sensors are connected to a gateway device, which collects data and sends it to ThingSpeak, which is a cloud-based server for analysis. In this system we have used sensors like gyroscope, ultrasonic distance sensor module, resistive soil moisture sensor, vibration sensor, DHT22 temperature, humidity sensor and microcontroller like ESP32. ESP32 is a low-cost, low-power system on a chip microcontroller with integrated Wi-Fi and dual-mode Bluetooth. A gyroscope PU6050 is a device used primarily for navigation and measurement of angular velocity. Gyroscopes are available that can measure rotational velocity in 1, 2, or 3 directions. 3-axis gyroscopes are often implemented with a 3-axis accelerometer to provide a full 6-degree of freedom motion tracking system. Ultrasonic distance sensor module is a sensor that can measure distance. It emits an ultrasound which travels through the air, and if there is an object or obstacle on its path it will bounce back to the module. Resistive soil moisture sensor. The soil moisture sensor is one kind of sensor used to gauge the volumetric content of water within the soil. A vibration sensor is a device that measures the amount and frequency of vibration in a given system, machine, or piece of equipment. Temperature and humidity sensor is a device that gives you a measurement of the temperature and humidity of a place. We have clubbed all the sensors together and made a compact system which consists all the sensors in it. The system is designed in such a way that it can study the environment, give us the real-time data, and durable for a longer period of time. The whole system is concealed and waterproofing has been done. All sensors are inside the plastic pipe, which makes the system more stable and secure. This system is placed in a soil container, which we have made a model of mountain terrain. Presently we have connected the model with power bank to provide the power, but as per future plans we will connect the system with solar panel. The server is responsible for processing the data and providing alerts and warnings to local authorities and residents when the risk of a landslide is detected. Then measured data is sent to a cloud called ThingSpeak. ThingSpeak is an AI analytics platform service that allows us to aggregate, visualize, and analyze live data streams in the cloud. The data collected from the sensors and modules is displayed using the ThingSpeak platform. The project may also include a web-based dashboard or mobile application that allows users to view the real-time data and receive notifications on their mobile devices. This can help local residents and authorities take proactive measures to prevent or mitigate the damage caused by landslides. Currently, our systems need Wi-Fi connection, but as per our future project we will connect the system with LoRaWAN, which will enable the systems to work offline over long distances. Overall, an AI landslide project can be an effective tool for early detection and prevention of landslides, reducing the risk of property damage and loss of life in affected areas. In this project, the data that is being gathered by the sensors is being transmitted through proper channel to a cloud server. ThingSpeak is the cloud where this entire data collected is being gathered and grouped together, which is automatically updated at a time lag of 15-20 seconds. The data grouped can finally be downloaded in the form of CSV, Excel or JSON file. Another important part of the project is the machine learning algorithm that is being used in order to make prediction based upon the readings gathered by the sensors. There are many types of algorithm available, but since this entire data is numerical and does not contain any category, so we used predictive algorithms instead of classification algorithms. The data that is available on the cloud is directly imported to the Visual Studio Code where the algorithm is being applied. The algorithm takes a particular factor such as vibration or humidity as the dependent variable and various predictions were observed. The entire phase is divided into two phases. Phase 1 prediction drawing stability, and it was observed that there was not much change in the reading, and hence this was finally labeled as the safe zone. Phase 2 is the time period when the readings changed due to vibration of underground moisture of soil due to rainfall. A very considerable change was observed at the time when land just moved. The readings were generated. Depending upon the sliding readings, a threshold value is being defined for all factors, and finally a category is defined at the time when readings changes and predictions made by algorithm reaches. Toward the threshold value, the alerts are being generated such as danger zone or evacuate the area landslide. The entire visualization of the readings changes in time can be observed in the graphs that are being plotted at the end. The entire process in which data is imported, prediction are made and visualization automated, and the entire script wherever gets refreshed itself, the new task session is being run and terminated. Items. The entire project is working in a real-time data and an overall lag of 8-15 seconds is observable. is working perfectly, and currently we are focusing on enhancing and calibrating our system to provide more accurate prediction results. As we have shown, our sensor data is coming on real-time basis on cloud, and then data moved forward to implement machine learning algorithm. At last, we come to visualization part. Some part of visualization is shown on ThingSpeak, and alert message as well as prediction graph and shown on Google Colab. As per future plan, we will create a live dashboard on Power BI, which will be composed of comprehensive analysis and visualization of all the graphs.